Should I start sharing my screen then?
Excuse me?
Should I share my screen?
Yeah, you may, yeah, please.
Okay, let's see if we get it going.
Okay.
Can you see it okay?
Yeah.
Perfect.
Yeah, we can see that. Okay. So, okay, welcome back, everyone. It's now my great pleasure to introduce to you our second keynote speaker, Dr. Laurence Rilett. Dr. Laurence Rilett is the distinguished professor of civil engineering at Auburn University and director of the Auburn University Transportation Research Institute. His research mainly focused on the intelligent transportation system applications and a large-scale transportation system modeling. Dr. Rilett has been a PI or co-PI on more than 40 research projects with total funding in excess of $50 million, funded by several different agencies, such as U.S. Department of Transportation, Nebraska DOT, Texas DOT, EPA, DOD, and NSF. And Dr. Rilett has authored or co-authored 100 refereed journal papers and over 100 conference papers based on his research. And he won 3 different prestigious ASC and TRB awards. He's currently the managing editor of the ASC Journal of Transportation Engineering Part A system. Dr. Rilett was elected president of the Council of University Transportation Centers for 2021 to 2022. The title of his presentation today is Forecasting and Estimating Transportation Metrics in the COVID-19 and CAV era. So please join me in welcoming Dr. Laurence Rilett.
Thank you, Dr. Fan. It's a wonderful introduction. So by way of background, I'm going to be talking about some of the work that we've done in the past 5 years on, wow, there we go. Give me 1 second. Okay, there we go. Sorry about that. I'm going to talk about some of the work we've done in the last 5 years. Our focus is going to be on lessons learned. So I'm probably not going to go deep into a lot of things, but more to give you some insight into some of the things we've learned about in some of the HCM 6, Highway Capacity Manual 6 work, particularly related to passenger car equivalence and travel time reliability. And then I'll provide some concluding remarks. So in terms of capacity and passenger car equivalents from the HCM 6, as you all know, passenger car equivalents are a way of translating mixed vehicle flow to equivalent passenger car only flow rates. They've been around a long time, probably as long as there's been highway capacity manuals. What's interesting about Highway Capacity Manual 6 is that instead of using empirical data to do these things for freeways, they use the VISM microsimulation model, in particular version 4.4. When we started the work, it was about 2 years after the HCM 6 came out. With the VISM 4.4 was no longer available. And so we had VISM 9, and first thing we had to do is make sure that the two were compatible. So we actually, everything you're going to see, we ran and made sure that the results that we were getting from VISM 9 actually measured what was produced in the HCM 6. They weren't going to be exact because simulation has stochasticity in it, but we did make sure statistically they were the same. So we're getting the same capacity values, the same capacity adjustment factors, the same PCE values. For those of you who aren't familiar, I'm going to just go briefly into how the HCM 6 did their work, or the developers did the work. They created a VISM model. They had a level section, they had a grade section, and that model had 3 lanes per direction. They had a percentage, they used single unit trucks and tractor trailers. They assumed that all vehicles go the same speed or have a desire to go the same speed of 70 miles per hour. And they used the VISM default values for car following. So they basically used, this was the approach they took. For those of you who are familiar with VISM, there's a lot of parameters. And I'm just putting up the slide to show you, yeah, there's a lot of parameters, and I'm not even showing them all. But if you're going to replicate what the HCM6 does, you really have to understand or know what they were using. One thing I did want to highlight, in their analyses, when they developed HCM6, they actually developed it based on an aggregation interval of 1 minute. To my knowledge, this is the first time the HCM ever used anything different than 15 minutes to calculate capacity values. And I'll come back to why this is important later on in the talk. So essentially what they did, developers did, they developed a number of scenarios. They had passenger only conditions, 13 grade levels and 7 distances. So that was 91 scenarios. They had 13 grade levels, 7 distance, 13 truck percentage, and 3 truck composition levels. That gave them 3549 scenarios for a total of 3,640 scenarios. So they did a lot of simulations to get to what was in the HCM. And you can imagine this is not a small thing to do. When we did it, we actually went through and automated everything. You can only imagine having someone try and run these one after another on Visum. To give you an example, how it works, how the PCs were calculated, I'll take one example. One of the scenarios, 20% trucks, truck composition level, 30% SUT, and 70% tractor trailer, grade level 3%, grade distance 1 mile. So if you go to the HCM, you can look up the PCE value for that situation. Essentially, they got the capacities values from the Visum model. So they ran Visum, in this case for passenger cars only. On the y-axis is flow rate, on the x-axis is density. You can see the relationship between flow rate and density, a very typical one from a simulation model. And they got the capacity out, 2268 vehicles per hour per lane, in this case, passenger cars per hour per lane. The thing to note about this graph is that in the analysis and in the HCM6, when they did it, they defined capacity as the 95th percentile flow rate rather than the 100th percentile, the maximum. Again, this is the first time that I'm aware that they used a different definition of capacity within the HCM. I'll come back to that in a bit as well, but we were replicating what the HCM did. So you did it for passenger cars, you then run the simulation for mixed traffic, again, flow rate versus density. You find the capacity, in this case, the 95th percentile value is 1764 vehicles per hour per lane. You then calculate the capacity adjustment factor, which is just the ratio of the two, it's 0.78. Once you have the capacity adjustment factor, you can use the equation to calculate the passenger car equivalent. So for this example, what the HCM procedure would say is that based on the simulations, one truck is equal to 2.43 passenger cars when you're looking at traffic flow for this situation. And of course, they did it for all those different scenarios and came up with different PCE values. It's a bit more complicated than I'm putting on. If you look at the way they did it, it was a 5-step process. I just described the first 2 steps. So they went through, did all those flow plots, they got the capacities, calculated the capacity adjustment factors as I showed. It turns out that those capacity adjustment factors have a bit of variability in them. Well, actually a lot. They weren't very smooth, so they then decided to go through and smooth them out by using a regression model. It was a fairly sophisticated regression model. I had 15 parameters, so I'm not going to go into it. It's in the literature on how they did it. When I first saw how they were doing it, I thought, why didn't they just put the equations in the HCM? And then when I saw the equation, I said, well, it's obvious why they didn't. We're not going to go and calculate, use 15 parameters to calculate CAF for PCEs. Once they had the formula, they could then calculate the CAF for all their scenarios and then calculate the PCE. And that's what's in the HCM6. So when you go and look at the tables for passenger car equivalents, this is the process they followed to get those numbers. And again, the interesting thing about this is the first time they use simulation to do this rather than empirical numbers. You can see the advantages. You don't have to go out and collect all those different amounts of data, right? The simulation allows you to do this, I'll say, relatively quickly compared to going and collecting empirical data. The HCM6 was based on East Coast assumptions. So it was 3 lanes. The model, the Visum model, was for the East Coast. And we had a question about what about the rural Midwest? What about places that didn't have 3 lanes of traffic? And our focus was Nebraska, because that happened to be where I was working at the time at the University of Nebraska, Lincoln. We went out and collected a lot of data on the interstate there. interesting thing about the Western US is that there are high truck percentages. So for the where we were collecting, they ranged anywhere from 20 to 45%. For those of you familiar with the HCM, you know that the PCEs only go up to 25. So we were well beyond that in a lot of our data collection sites. And there are places in the Western US where the truck rates are even higher. What did we find? Well, we looked at free flow speed distribution. Remember, the HCM assumed it was one value of 70 miles per hour, essentially. For the passenger cars, the average was 72 miles per hour. And out west in Nebraska and west of that, the typical speed limit on the interstate is 75 miles per hour. So this isn't all that surprising that the speeds were high. This is the speed limit for single unit trucks, or speed distribution. This is the speed distribution for heavy trucks, the big tractor trailers. And what you notice is that there's a big differential between the trucks and the passenger cars. The reason for that is that in the United States, most of the trucking firms regulate their trucks. They limit their truck speed to about 67 or 68 miles per hour. That's for economy reasons. It's for saving fuel and cost. So we have this sort of dichotomy where you have a high speed limit, but the trucks are actually going much lower than the speed limit. And you can see that visually on this graph. The effect of that is that you tend to get moving bottlenecks. You can imagine having two trucks, one going 68 miles per hour, the other going 67, and the 68 mile per hour one decides to pass the 167. This takes miles. It takes minutes to make that maneuver. And in the meantime, all the cars get stuck behind them in these sort of moving bottlenecks. On the left, you can see a video of it. On the right, you can see the simulation of it. So what our goal was to do is to go through and estimate the PCE for Western US conditions. So we wanted 2 lanes. We wanted our tractor distribution. We wanted to use the speed distributions we were seeing. And we wanted to calibrate the model to what we were seeing in the field. And we did all that. This was the result. So on this graph, so this is the passenger car equivalents using the VISM approach, or the HCM6 approach. On the y-axis is the passenger car equivalents. On the x-axis is truck percentage. The different lines are based on different distances and grades. I'm not going to go into them, but basically the green one shows the HCM6 values, which comes out to about 2 per truck. So each truck's about 2 when you look at, on average, when you look at the HCM6. In the Western US, the equivalent ones are above that in the red. And you can see that, it varies based on truck percentage, but they're about 54% higher. Okay, so that what we're seeing is that the HCM6 values, if you followed it in the West, if you followed the HCM6 procedure in the West, they were 54% higher. There's a number of ways of taking this. You could say, well, the HCM6 doesn't really apply. I sort of take it as an approach is we now have a tool that we can apply for our own conditions. And so instead of having one set of passenger car equivalent values, for example, you can put it down to your own region. This is our region. These are the type of things we have. It's not equivalent, Nebraska is not equivalent to New York, for example. You can also go through and look at different things. Our speed limit was 75. There are places in the US with higher speed limits, 80. There are ones with lower, 70 miles per hour on these 2-lane Western roads. And you can see what happens. There's the passenger car equivalent. There's the HCM6. And as you'd expect, as the speed limit goes down, the speed distribution goes down, the closer the PCE values. If there's a higher speed limit, then you get a higher PCE value. And that's sort of what you'd expect. This other graph looks at data aggregation. So this is the PCE, the passenger car equivalents on the y-axis, truck percentage on the x-axis. The blue line shows the HCM6. The top orange line is 1-minute aggregation. So we took the same data. We didn't change anything except how we aggregated and calculated capacity. Okay, so you could do it 1 minute, you could do it 5 minutes, you could do it 10 minutes, 15, 20 minutes. And as you'd expect, the bigger the aggregation level, the lower the capacity value, and it affected the PCE, the lower the PCE. So depending on how you define aggregation, you actually get different PCE values, which is why it's really important to make sure you're using one that's sort of consistent across things. So what are the lessons learned on what I just talked about? Well, we're now gone to this world where we're using simulation to model the HCM parameters and metrics, right? So there's questions that come up about repeatability and simulation. You know, if the VISM changes, do we actually have, can we go back and check things, or are we just sort of stuck with the VISM model we used? Obviously, if you're going to use this, you have to know the parameter values. You not only have to know what VISM model you're using, you have to know what parameters were used in the simulation. So there's a big issue on version control. I think there's a big issue on extrapolating things that were done on the East Coast to other locations. So our argument, or my argument, is always, well, you should calibrate your models. You should validate them for your area. In our case, the local conditions in the Midwest. The future, right, the connect, sort of what I was talking about in the title, connected and automated vehicles. Well, VISM 20 allows you to model connected and automated vehicles. And I guess I just wanted to point out that you have to be really careful about just picking VISM 20, running it, and then comparing it to the HCM, because there are version control issues, and I'll talk more about that in the next few slides. I also wanted to point out that, this 15 parameter model is pretty complicated. We actually went through and took all our data and said, can we come up with a simpler model? And we came up with one that had 6 parameters that looked at the percentage of trucks, the truck length, and the grade, the grade length and the grade itself, and came up with one that's fairly simple. When we compared it on the y-axis to what's in the HCM and on the x-axis to what we were doing, we had a 99.99% fit rate, R-squared value, an error rate of 0.64. So you actually can go through, use these data and come up with simpler models that you could then use, for example, to do your passenger car equivalents. So if you didn't want to extrapolate the numbers that are in the current HCM6, you could use this model. So getting to the compatibility issue, one of the things I wanted to talk about was VISM 4.4 is no longer available. That's what the HCM6 was. We just discussed previously that when we compared it to VISM 9, it worked really well. They gave statistically similar results. However, when we looked at VISM 11 and VISM 20 further releases, when we looked at them on the modeling on mixed traffic, it worked out well. It compared very well to 4.4, but on the passenger cars, it didn't. So on the bottom graph here, you can see the red is VISM 9 or VISM 4.4 type results and capacity. On the left is depending on whether you're using 95% capacity or 100%. But the key point is that the orange and the blue, that's VISM 11 and 20, don't compare well to VISM 9. So if you just took VISM 20 and ran it and did the whole capacity thing again, you could get into trouble if you're comparing it, right? So we kind of had an issue. So when we looked at connected and automated commercial vehicles, we took the passenger cars as VISM 9 because we knew that. So we took the capacity values because we knew that compared well to HCM6. We knew VISM 20, the mixed flow, worked well to VISM 4.4 and VISM 9. And then that allowed us to go, well, let's look at what happens when we do connected vehicles. We know we can replicate what we were doing before. Let's see what happens when you do connected vehicles. And that's what we essentially did. We were assuming all trucks were operating as CAVs. We assumed 100% market penetration. We took a platoon size of 7, and we compared what would happen for the CAV using the HCM model. And this is the results. We have the passenger car equivalents on the y-axis. On the x-axis is truck percentage. We have a number of combinations. You can look at, 0 grade, different grades, different grade lengths. That's what it shows. On average, it was 34% lower. I don't want to go into every combination because that could take, an hour looking at all these things. But I wanted to get across a couple of points. Obviously, the CAVs increased capacity. In our analysis, it was 34% on average. Again, it depends on the grade length, percentage of trucks, and we did all of those type of sensitivity analysis. There is a paper out on it, and I put the thing there if you want to go out and find out more. I think what I really wanted to get across is that, yeah, you can measure CAVs, but you have to be very careful to compare apples to apples, right? If we had just taken VISM 20 and ran it, we would have gotten different results when we compared it to the HCM than the way we did do it, because we had checked to make sure that it was compatible, but to the earlier versions. So, you know, the change. So the question is, if we had done that, would the changes have been due to the CAV or the changes in the VISM code? And that's sort of a warning for everyone, right? Other issues that come up, you know, common definition of capacity. I've always argued we should stick with the capacity. If it's 100% through the HCM6 or the HCM, it should be that way everywhere. And if we're using 15 minutes everywhere in the HCM, we should probably use it in this analysis as well. Again, these are lessons learned probably for HCM7. So as we go forward, you know, how do we keep track of compatibility between versions of VISM? If we're going to continue to use simulation, how do we make sure that we're comparing apples to apples? How do we make sure that we have the right definitions of capacity and aggregation? And how do we validate the simulation? How do we know, calibrate and validate the simulation model for our local conditions? The second thing I wanted to talk about in terms of metrics is still the HCM, but looking at the travel time reliability. There's a lot of definitions. I'm just going to take the HCM 6.1. So historically, we've measured system performance by point estimates, mean travel time, 95th percentile travel time. Recently, I'll say the last 10, 15, 20 years, we've moved into travel time reliability. Lots of definitions. I can give you 4 or 5 off the top of my head. The HCM6 talks about travel time reliability reflects the distribution of trip travel time over an extended period. It's a function of weather events, incidents, work zones. They've actually come through and created a new travel time estimation methodology for arterials. This is an important step forward, right? Before with HCM, we only did mean. Now we can do mean, variability, and reliability performance measures, and I'll talk about that in the next few slides. Here's what's interesting about the approach in the HCM6. They put in the methodology, and in talking with the developers, they never actually went out and compared it to empirical data. So the approach is pretty straightforward. They have a way in the HCM6, as you know, of estimating travel time. What they did was they put in a Monte Carlo simulation where they said, tell us how many rain days a day or snow days you have. Tell me how many incidents you're going to have. Tell me how many, you know, demand, what's your demand variation like? You put all of that into their program, and you say, I'm going to do weekdays through the year from AM peak, and it'll go through and it'll estimate a series of travel times, and you get to choose if it's 15-minute or 1 hour. But the end result is you come up with a travel time distribution. So you can go through and estimate a travel time distribution, and from that you can calculate your travel time reliability metrics. Okay, so very straightforward way of approaching. If you have all the information, you can use it to forecast, or you can use it to back estimate. And because we had a lot of information, we can actually go through and check to see how accurate it was. We know how many, for example, on a certain quarter, how many snow days we had, how many incidents we had. We know what the demand, or sometimes we know what the demand is. So we can go get our own travel time distribution and compare it to the HCM, which is what we did. So in the travel time data collection in the US, historically it was done by government, speed detectors, loop detectors, you know, radar, video. Increasingly, it's the private sector, cell phone location, Bluetooth data. There's a number of companies out there, Streetlight, ClearGuide, INREX, that do it. I'm going to be using INREX data today, but any of them could be used for what I'm talking about. This is Dodge Street in Omaha from 2019. We went and collected all the data, and we ran the HCM6 reliability. This is a cumulative density function, distribution function. This is the average 15-minute travel time for the AM peak. And this is the estimate from HCM6. Looks nice, mean of 4, standard deviation of 0.22. We then went out and got the INREX data for the exact same corridor for the same thing we were modeling. And we got that. So mean was close, standard deviation was not close. We did this for 9 other corridors throughout some urban areas, very high density, low level of service during the peaks. And none of them fit. Nothing really worked. We did go through and find a way to calibrate it. So we could calibrate the model. And so that can be done. And it's I'll give you the reference for that. But the interesting thing was we could not use the HCM6 travel time reliability model and get results that even look anything like the empirical ones. So lessons learned, we're no longer measuring performance by a single measure. That's probably a good thing. Reliability is a function of travel time. There's no clear definition, but it has to do with the mean and variance and 95th percentiles. HCM uses simulation to model the travel time, but it wasn't calibrated to any empirical data. So, I'd caution you from using it without checking whether it's valid or without validating it for your area. Okay, and the good thing is now we have lots of travel time data. You can, and if you have travel time data, you can actually calibrate it. And I gave you the reference on this slide. So going from travel time measurement using HCM6, what I want to do is finish off with the COVID-19 pandemic and travel time reliability. We had the pandemic, there was a lot of things that went on. Is travel in the US roadways safer? Well, a number of deaths went down, but crash rate went up, right? Because the number of deaths decreased slower than the decrease in volume. What we were interested in looking at was whether the travel time reliabilities was actually better, whether the travel time is more reliable during the pandemic. But more importantly, we wanted to look at what metrics were best at capturing this. So let me show you an example. We used INREX travel time data. We used AM peak, PM peak, 15-minute subperiods. We used average travel times. And we looked at March, April, and May, the height of the pandemic 2020, and compared it to 2018 and 2019. So we looked at we looked at 4 corridors, 2 peak periods, 2 directions. So we looked at 16 scenarios. This one I'm showing it is Omaha Dodge Street, 3-mile section. It's part of the national highway system. I'll explain why that's important in a minute. And the max AADT was about 80,000 vehicles, so peak level service was out. So it's a pretty congested arterial roadway. This is a box plot of the data from 2018 and 2019. On the y-axis is average 15-minute travel time. So you can see 18 and 19. You can see the dark line is the average. The box is the interquartile, 25 to 75%. The lines are 5 to 95%, and then those circles are just outliers. And you can see in 2018, 2019, they were fairly similar, had about the same range. There's some more outliers in 18 than 19, but fairly typical. The next slide shows what happened in 2020. And there's 2 things you should notice. One, the mean dropped, and it dropped fairly significantly. It dropped about 16%. More importantly, the standard deviation dropped. There was less variability in travel times, which you'd expect from a loss of volume, and it dropped about 46%. We looked at this across, this is typical, the one I just showed you. We looked at all 16 scenarios. The average drop was 14% in mean. The average drop in standard deviation was 43%. The coefficient of variance, which is a measure of the spread to the mean, dropped 34%. So our conclusion, no matter how you define travel time, it was more reliable during the pandemic, right? Regardless of the definition. I don't think anyone's surprised by that. We had much less traffic. Your travel times are going to be more reliable. They're going to be lower and with less spread. Right? What we really want to do is look at the metrics. So US transportation agencies don't tend to use those common metrics I just described, mean, standard deviation. The argument is that users don't understand them. So people have created a wide range of metrics, travel time index, planning time index, and I'm going to talk about these in the next few slides. Travel time index is simply the mean travel time over the free flow travel time. So how much more time will I need to travel a quarter compared to free flow conditions, right? If you look at the formula, it only considers mean travel time. If you look at the difference during the pandemic, the average drop was 14%, which was the same as the mean analysis. And it makes sense. The only thing changing is the mean. So if you're looking at travel time index or you're looking at mean and you're comparing them from year to year, it's the same analysis. It's not going to change because the travel time index is just a mean divided by a constant. Planning time index is similar. On the numerator, on the numerator, there's a 95th percentile travel time, still divided by the free flow travel time. It's trying to capture how much longer you have to get there if you want to be on time 19 out of 20 times. It dropped during the pandemic by about 20%. So again, you're still getting this idea that there's more reliable. The level of travel time reliability metric is defined as the 80th percentile travel time over the 50th percentile travel time. This one's important because it's used by the US National Highway System. So I just showed you an example from the US Highway National System in Dodge Street in Omaha. So this is required by MAP 21, by the FAST Act. This is how we measure reliability in the United States on our national highway system. If you look at these numbers from 2020 from the pandemic to the non-pandemic, the average drop was minus 3%. So it went down, but only 3%. Why was that? It turned out that the 80th and 50th percentile both decreased at about the same rate. So while they both went down, they went down at about the same rate, which meant there was no change in travel time reliability if you want to use this metric. And I say no change, 3%, very little change in reliability. So if you use this metric, you'd say, oh, there might not be too much. The last one I want to talk about is the buffer index. It's a measure of spread, 95th minus the mean divided by the mean travel time. It's a measure of dispersion, the measure of central tendency, very similar to the coefficient of variation I said earlier. And not surprising, it had the same kind of drop as the COV, about 34%. And remember, the argument is people can't understand the COV, but they can understand the buffer index. They're essentially measuring the same thing. So I'll let you decide whether that's a true statement or not, and people can't really understand it. So the arterial roadway is more reliable. Well, if you average across all 16 scenarios that we looked at, you can see it depends on what metric you use. And again, the interesting one is that the LOTTR, which is the one used by the federal government to measure reliability, actually showed almost no change in reliability during the pandemic. I would argue, based on the results I just showed you, there was a huge change. Not only did the mean drop, but the variability dropped a lot. So lessons learned, profound. COVID-19 had a profound effect on the transportation system. It's a natural experiment. So how do we measure system performance? Crash rates up, are we less safe if the number of crashes are down? Travel time reliability, it was the same if you use the LOTTR. So the lesson I take away from this is reducing complex systems to simple metrics can be misleading sometimes. So know your data, know your statistics if you really want to make meaningful insights. And so we wanted to show from the COVID data, you can actually identify which metrics you kind of prefer for identifying reliability. My bias is always towards statistical measures, mean, variance, coefficient of variation, because they have very defined meanings and we have very good ways of measuring, not only measuring them, but in making inferences about them. In closing, I always go back to tell my students a famous quote from George Box. Essentially, all models are wrong, but some models are useful. I think looking at the HCM6, we're in a great opportunity. We have great data, we have great simulations, new ways of doing things. And I think it's up to us as a group, as a profession, to make sure that those microsimulation models are useful for the applications we're doing. Are they calibrated? Are they validated? Are they internally consistent? You know, we have a lot of opportunities to do things differently and better than we have in the past. And I just want to, that's sort of what I want to end on in my talk. Acknowledgements, of course, we got a lot of data from City of Lincoln, City of Omaha, Nebraska DOT. There were a number of papers that I referenced in here. The reviewers' comments were great. I have to thank my students, Jianming, Zhou, Ernest Tufor, Antonio Herbel, Li Zhao, who worked on it as part of their PhDs. Sean Murphy worked as part of his master's. I have to thank the HCM6 developers. They were very generous in explaining how things were done and how they approached the project. Again, I think this is a great emphasis on how well things are going, that we're doing all these new and innovative things. And I also want to thank them. And I'd also like to thank everyone who's listened. I know I gave you a lot and I didn't go as deep as we might have, but I did want to try and cover a wide range of things that had similar aspects. So with that, thank you. And if you have time for questions, I'll be happy to take them.
Okay, thank you very much, Larry, for your very interesting presentation. We really appreciate your time and support of CAMMSE, and glad to have you here today. So at think we do have a couple of minutes, maybe for 1 or 2 questions here from the audience. So any of you have questions? I do not see any from the chat box. So maybe here from the audience, maybe you can raise question if you have. Okay, for Dr. Rilett.
I must have done a great job, so I'll thank you for that.
Yeah.
I think the only thing I want to again point out is that this is a great opportunity for students to really look into these new models and take the data and really come up with models that apply to local conditions. So
yeah,
that's sort of the takeaway I would get across.
Yeah, thank you, Larry. I have one question for you actually. So are you aware of any rationale behind the thing for them to use the 95th flow rate as the capacity?
Yeah, I think, again, I don't want to speak for the developers, but it's my understanding, and I kind of get it. When you're using simulation models, you get a lot of variability in results, right? And so what we tend to do is we tend, at least in my group, we tend to run the model maybe 10 times and average it, because depending on your random seed, you can get kind of funny results sometimes. Sometimes things just happen. So I think the reason they went with 95th was to take out some of that variability in their results. I personally don't think it matters too much which one you use, as long as you're consistent. And my argument, so we had gone through, when we had all the data, we looked at both 100% and 95th%. I believe you can calibrate the models to the point that you could use 100% and keep the data, keep the analysis consistent. Similarly with the 1 minute aggregation, it just means, the reason I think they went to 1 minute is that they could get a lot more data points. My argument would be keep it at 15 and run the simulation longer to get the same number of data points. But again, when you're talking about 3,600 scenarios, that's a lot of work. You really have to automate it. So that's a long answer to a short question, but that's why I believe it. I believe it's the natural variability of the simulation. That's why they did it.
Okay, yeah, thank you. And I see one question, a couple of questions pop up just now. So one question is Dr. Mockmill. Dr. Mockmill, do you want to ask question directly yourself, or I can do that for you here? Okay, so he's probably muted. So Dr. Mockmill's question for you is, how about regional variability? You talk about Eastern versus Middle West. What about other regions? Yeah,
that's a great question, Randy. And I think that's sort of the point I wanted to get across in this. We looked obviously at our area, the Midwest. You know, I lived in Texas for 10 years. I would bet that the Texas numbers, if you took the same approach with the HCM and ran it there, you'd get different. If you calibrated your model to Texas conditions and then did the same HCM study, I think you'd get different PCE values. Certainly on Western Texas, you have 80-mile-per-hour roads, and I think that would affect things, particularly on those 2-lane. Now, I haven't gone and got the data myself. I think this is what the great thing about this, there's issues with doing simulation models, but one of the great things with simulation models is you can actually calibrate and validate it to your local conditions. And if you think it's important, and certainly where we thought it was important, I think I won't say it's easy to do, but you saw the methodology, you can go do it. So I personally would think that there are differences in Texas, in California, the drivers are different. I believe you would come up with different metrics for each region, but I have not gone and done that analysis.
Now, can you hear me now?
Yeah, I can hear you, Randy.
Okay. Yeah, I think you're exactly right. As you were talking about this, I was thinking about Texas, and I said, I bet Texas is probably different. And in fact, I bet Texas is regionally different, the West versus the eastern part of the state.
Yeah.
So anyway, thank you very much. Good, excellent presentation.
Well, thanks, Randy. Yeah, I'd love to see what those things are. And like I said, what I don't want to do is come and say, oh, be really negative on the approach. I think the approach is great. I think it's an opportunity for all of us to really think about validating, calibrating models for our local area, and we have the data now. So this is this is a real opportunity.
Okay, thank you, Larry. The other one actually is not a question, just a comment made by Xuesong, Simon Zhou from Arizona State. He said, Larry, thanks for a great talk and the motivation of data-driven approaches on the key issues of fundamental diagram and travel time delay definitions.
Well, thank you. And if anyone else has any questions or wants some of the references, I'll be happy to share them with you. Like I said, it was a pretty broad talk from a lot of different things. So if you want details, feel free to reach out.
Okay. So thank you very much again, Larry. So at this point, we're going to take a maybe couple minutes, very short break. We are going to come back at 1:45, and we'll be having our invited speaker session on connected and automated vehicle. So see you in 2 minutes. Hey, Dr. Mark Mill.
Hey, Randy, good to see you.
Good to see you.
So thanks, Wei. That was great. Appreciate the opportunity.
Yeah, thank you, Larry. Glad you're here. Yeah, with us.
I look forward to seeing you in person soon.
Yeah, hopefully in TRV, right? Yeah.
Hey, Wei, can you hear me?
Yes.
Somehow I could not start my video.
Okay. So, Shaoji, can you maybe give the permission, Dr. Park? Maybe he can share the screen, or
Oh, I can share screen. The video I could not turn it on.
I see. So we have one student. His name is Shaoji Liu. So I can write down here.
Oh, okay,
He's
it
working on
works
that.
now. Thank you.
Yeah.
Because he made me as a co-host.
Okay, good. Hey, Brian.
How are you?
Good, how are you?
Good to see your face.
Yeah, good to see you. Long time, huh? No see.
I know it's a pandemic.
Yeah.
Hey, Larry, how are you?
Good. Very well, Brian. Good to see you.
Yeah, you too. Congratulations on your new position.
Oh, thank you. Yeah, we're excited by it. It's
further
good
away from
opportunity.
Canada, though.
Yeah, that's in November, December. It's a good thing.
I thought your home is in Canada, hometown.
Right. Yeah, my home. Yeah, my hometown is Windsor, Ontario, right across from Detroit.
Oh, right, Detroit area. Yeah.
Yeah. So I'm not going to miss the snow. I'm not going to.
It's good.
Okay. So 1:45. I think we can get started. Okay. Good afternoon, everyone. So now we're getting to the invited speaker session on connected and automated vehicles. So as we all know that the connected and automated vehicle technologies are expected to transform the nation's transportation system over the coming decades, with enormous implication for the planning, design, and operation of cities and regions. There are a lot of challenges and opportunities pertaining to transportation policies that may arise as a result of such emerging CAV technologies. So to help us better understand these challenges and opportunities, we invited 4 outstanding speakers who are CAV experts and generous enough to share their time and expertise with us today. So we appreciate that. So with that, I'd like to begin. There's a little reshuffling going on here. We're going to switch between the first speaker and the last speaker. So now it's my great pleasure to introduce to you our first invited speaker, Dr. Brian Park. So Dr. Brian Park is a professor of engineering system and environmental department and a member of a Link Lab at the University of Virginia. And Dr. Park is a recipient of many IEEE ITS, PDV, and ASC, as well as CATC awards. He's an editor-in-chief of the International Journal of Transportation, an associate editor of the ASC Journal of Transportation Engineering, Part A system, and KSC Journal of Civil Engineering. So the title of his presentation today is cooperative platooning along with human-driven vehicles. Now, please join me in welcoming Dr. Brian Park.
Thank you very much, Wade. That's a very nice introduction. I am truly honored to be invited and share my research on connected and automated vehicles. Hopefully you see my screen pretty well. Anyone
Yes.
get it? Great, thank you. This talk is about with the human-driven vehicles. Obviously, we love to see automated vehicles going around, and then they do form CACC and then best efficiency. I see that as not a near term, it's going to be a long, long time. So research I wanted to do was, can we do better cooperative platooning as of today with the human-driven vehicles? So the first, I want to tell you about cooperative adaptive cruise control, and most of us know what this is about. We have ACC, which is adaptive to conditions of preceding vehicles, very helpful for stop and go conditions, but it doesn't have efficiency that need to have move like a train. They have up and downs of adjusting speeds and then depending on sensors and conditions of the leader vehicle. When we have a cooperative adaptive cruise control, this is a really good for efficiency because study has shown that in the field, the cars can go as 0.6 seconds apart. And typical 1.8 seconds, we are basically tripling the roadway capacity. So connectivity is great with the autonomous vehicles. So that's the idea of having cooperative platooning. I want to show you why we want to do CACC over ACC, even though it requires communications, more devices, and mostly downside of ACC is that if you are doing ACC with the 1 or 2, maybe 3 vehicles, it's okay. But if you have a 4, 5, 6 vehicles on the screen in the left side, they have a so-called accordion effect. If you have like a 4th and 5th, you're not really able to follow closely, and then you get a lot of oscillations in accelerations, and you get very uncomfy, and which is not good for platooning. So ACCs, they're not really designed to have a platooning and have efficiency. CACC does, as you can see here on the right-hand side. Cars can actually move like more like a train, and then has huge efficiency in terms of fuel savings, better dynamics on the wind, things like that. So it's good. When do we expect to see 100% fully connected and automated vehicles? Because to do CACC, every single vehicle has to be connected and automated. And this is from a leading market research firm doing it. So optimistically, sales is probably better chance of having automated and connected vehicles instead of all the vehicles in the field outside. So even with the top higher sales level predictions, it's going to be very, very long time to reach close to 100%. So that means we are stuck with the human-driven vehicles for many, many decades. So doing research what I do should be important. The reason I want to show this picture is that when we have a platoon of connected and fully connected and automated human-driven vehicles, connected and human-driven vehicles, we were able to do CACC, but whenever there's a human-driven vehicle inside a platoon, I should have done this mode. When we have a human-driven vehicle in the platoon, this will create sort of interference to the connected vehicles. Even though this vehicle is fully connected and capable of doing CACC, it has to fall back to adaptive cruise control, which will have a downside of things I mentioned. And if you look at this as a whole platoon of vehicles, there's a fully connected and automated vehicles, and also there's a connected vehicle driven by humans. And they are not really gaining benefit. So CACC capable by running into unconnected vehicle, forced back to ACC. You are connected and human-driven vehicle. You're not gaining much because you don't have anything to getting from the preceding vehicles. Situation like this. If it's ACC, you are connected, but you cannot really have a benefit of getting, I am braking, you should do it smoothly. You cannot. So there's no benefits. So the goal of this research was, we want to design a system, even though I don't have a preceding vehicle as a connected, further downstream should have a connected vehicles. Can I take advantage of that vehicle and have some connectivity from further down and doing similar to CACC? And also, you as a human driven vehicle, but having connectivity, and if you're getting something from preceding vehicle, what can you do about it? And can you do better than human as driving conditions? So the goal is developing two algorithms and try to improve cooperative platooning along the human-driven vehicles. So that's the idea. I want to show you the so-called CACC with the unconnected vehicle. This is a very common scenario until we have 100% market penetration rate. I don't want to go in depth about detail, but the idea here is we have an ego vehicle, which is a connected and automated vehicle. And it's the first preceding vehicle is not connected, whether this is an automated vehicle or not. Best thing we can do is ACC, having sensors and then try to do. ACC is also a feedback control. So we have some sort of feedback control running. And then further downstream somewhere, it could be N+1 preceding vehicle. If it has a connectivity, even with the connected human-driven vehicles, this vehicle can send its intended acceleration, deceleration information, and it can be used as a feed forward signal. And there's a feedback control going on and feed forward signal. By combining these two, somehow we can make this one doing better than ACC. That's the idea of a CACCU. We make it as a linear time invariant system for easier control. Biggest black box is that we have no way of knowing how humans are going to be behaving. Luckily, there's a knowledge of knowing humans' typical headway, human delay in responding. And on the CAV followings, there are two parameters for doing the human gains. These are typical. And what we are designing is that we want to consider this as some sort of a CAV following model, predicting the behavior based on so-called optimal velocity model. When we predict, we know there's errors. What we are trying to do is so-called string stable conditions. So we can optimize control of this feedback and feed forward signal control based on humans' behavior. And we were able to do about 97.5% of time. Humans are trying to hit the it's a preceding vehicle, or slab on brake trying to hit to the preceding following vehicle. That's probably about 2.5% of time. Other than that, we were able to optimize and maintain fairly short headways. Depends on the humans' actuation delays and time lags and others. This varies. We were able to maintain headway less than 1.05 seconds to make a so-called string stable conditions. It's a very important term in mechanical engineering. Cars maintain, without going much higher speed than its a preceding vehicle, it maintained the string stable conditions. And when ACC alone was used to make a string stable conditions, research found that it's about higher than 2.6 seconds. So maintaining string stable conditions with our control logic, almost 97.5% of the time, which is what human does most of the time, we were able to maintain much shorter time headway and then making it work as a string stable conditions. So that's the essence of the algorithm. We want to test out this algorithm using real world data. So first thing we did was using NGSIM data. NGSIM data has about 620 meter long, tracking each individual vehicle. So what we were doing is that we could have a 3 vehicle pair and then going through the entire area. And we take a first 2 vehicle as a connected and unconnected vehicle. And then third vehicle, it could be human driven. It could be our ego vehicle doing ACC or CACCU algorithm that we developed. And one thing I want to point out is that we are using so-called vehicle dynamics model. That's a pre-scan. It's an off-the-shelf commercial tool. The reason we are using this pre-scan is that if we are using BISSIM or typical microscopic simulation model, as you know, it's basically adjusting acceleration based on safety distance or maintaining desired speed, which is not like a real world, real car behaviors. Real car, as you know, low level control, you have a throttle level change and braking changes. It has a different way of propagating the power to the vehicle. So we have to mimic those to realistically model this kind of CACC behaviors. So that's one important difference from typical evaluation done in the microscopic simulation level. So here are some results. When we use about a couple of hundred pairs of vehicles along the freeway of NGSIM data, we only compared here under the ACC consumption. So if you don't have a connectivity, even if you are connected and automated vehicle, you have to do ACC. And if we have assumption about there's a further preceding vehicle has a connectivity, even though immediate preceding vehicle has no connectivity, we are able to use the CACCU algorithms, and these bars are comparing how much better over ACC. So overshooting is trying to catch up with the maintaining similar stable conditions. So not doing overshooting is better. So we reduce almost 60 to 100%, a lot less on acceleration changes, spacing errors are better. So everything is better, and we could save, depending on situations, 3 to 7% fewer savings. So this is good. One thing we did was, this is another way of looking at it. If you look at so-called string stable conditions, overshooting is like here, you are doing much higher speed than preceding vehicle to catch up. And then this will create unstable conditions. And our CACCU has a much smoother way of following preceding vehicles, and that maintains a better stable conditions. We really want to do this with the actual field test, because when you use a simulation, people see a value of a potential, but unless this is done in real world, it's hard to quantify benefits. Challenge of real world testing, at least in the US, is that UVA doesn't have the car. So I had a time spent at the KAIST in Korea, and they were able to do some testings that we are proposing. So we are working together on this one. They had 2 autonomous vehicles with the connectivity. As you know, we need 3 vehicles. So we are able to do this with the 2 vehicles. If you think about it, I think this is one innovation we are adding to the experiments. In the mechanical automated vehicle world, they can actually record the vehicle maneuvers. So they basically record how vehicle moves. They can repeat the same exact conditions. Small changes are tire pressures and road surface friction factors, but exact command of doing accelerations are given, brakings are given. So we are identifying conditions as almost identical situations. So that's a good thing. So in that way, we really don't need a second preceding vehicle, because all this vehicle does is that it's acceleration and deceleration command as a feedforward signal to the ego vehicle. And then ego vehicle is using sensors and ways of understanding its immediate unconnected preceding vehicle, what it does. So we are able to mimic, and also under ACC mode, human-driven mode, CACCU mode of ego vehicle, we have exactly same condition of first and second preceding vehicles. So this was a really good thing to try. But if we didn't have this, just using 2 vehicles, real world, we might have to do a lot of runs to make general observations. So this was a good thing to try out. And we were able to do that for 2 scenarios we borrowed from NGSIM trajectory, realistic trajectory, and we are actually doing that for first 2 vehicle mimicking same trajectories. And under the ego vehicle, we are doing CACCU, ACC, and even human drivers. So humans are following the automated vehicle conditions, and multiple trial runs, and we are showing that how much benefits we are getting. So CACCU compared to ACC, about 60% better spacing error, 10% less than acceleration changes, 6.24% better fuel consumptions, obviously a lot better than human drivers. So this was a really interesting finding from real field testing. The next one is when you are connected and human driven vehicle, and you are not really gaining much in terms of a CACC because you don't have a fully automated conditions. You might have a simple acceleration and braking ACC type maneuver capable of in the vehicle. Can we do better than human doing following the connected vehicle? So that's the case. So if you think about human following, let's say, connected preceding vehicle, if it's not connected and human, basically the same thing, you are accelerating if you feel like you are too far away from the immediate preceding vehicle. So you're closing the gap, and then you're getting too close, you slow down. And humans do this all the time. And problem is the human is not perfect. So their acceleration, deceleration is always over undershooting and not maintaining string stable conditions. So our research is when immediate preceding vehicle is connected. So it can tell you what I'm doing as acceleration, deceleration. Let's call that as a feed-forward signal. If we can get that information, and we can potentially create complement adjustment to human drivers. So humans are doing over acceleration, and we know based on immediate preceding vehicles intention to accelerate or decelerate. Hey, you don't have to do that much of acceleration. We compensate that behavior to be optimal, so-called the string stable conditions. So this is a very simple idea. Mechanically, we actually have a human manual of what human intention of doing it. So human is doing gas pedal, and it tells the throttle level to accelerate, or on the braking, we understand how much braking it's gonna do. Whatever that is given, which is not optimal string stable conditions, we generate this function to be string stable conditions. So fairly simple, but the idea is that we help a human to be more efficient driving conditions. I'm not going to explain these equations. This can be done in a way of optimizing system equations. So we define those, and we minimize spacing error to be optimal string stable conditions. And we can adjust this function as a transform to the string stable condition of the domain, and we simply optimize and then find the best solution for human and compensating whatever's human's behavior. So this is one idea of how much we can improve in terms of string stability conditions. And as you can see here, this is a condition of humans sort of car following maneuvers. When humans are doing it, they never be able to achieve string stable conditions because of human. This is P as their headway. If a headway is higher than 1.2 seconds, human can react less than 0.6 seconds. They can actually create this say the string stable conditions. Human reaction time is longer than that, they cannot. When you use HCACC, because we can do adjustment of human behaviors, we can have a much larger area to make a string stable conditions. And even with the headway higher than 1.17 or something, about 1.2 seconds, regardless of human reaction time, we can make a string stable conditions. So it's a much wider area. We allow human sort of give intention, I want to accelerate, I want to decelerate, and our algorithm can compensate, or you're doing too little, too much, and we adjust that for you to make a string stable conditions. So that's the idea. And on this one, we were not able to do the field test, but we are using a driving simulator. Again, one of the driving simulator component we are using is vehicle dynamics-based driving simulator. When you give acceleration as a gas pedal, it actually software simulation-wise, the software that actually mimic low level of throttle levels and braking levels, and that transferred into the power into the vehicle dynamics. So vehicle moves at the different speeds or based on accelerations. So that's how we did it. I want to run a very quick short video. top is without having human in the loop CACC. Bottom is with the human in the loop CACC. As you can see, human, this is a driving simulator, so it's not perfect, but humans are doing too much acceleration and then too much deceleration. It's up and downs. With the bottom, whatever human intention you get, you are compensating to be optimal, string stable conditions. As you can see here, the trajectory from this video shows that humans and preceding vehicle, without having this algorithm, you get a lot of fluctuations. When you able to use this algorithm, you are basically following almost identical trajectory to be string stable conditions. So the benefit of this is that if there's a leader vehicle doing some sort of CACC conditions, stable conditions, you get much better stable conditions of driving behaviors. So that's pretty much what I want to share. Obviously, the algorithms, this is a very efficient and systematic way of doing platooning, cooperative platooning under human-driven vehicle conditions. So we are able to, we cannot do better than CACC, but we are able to do a lot better than ACC or human alone cases. So hopefully this can be useful for actual implementation before we have close to 100% market penetration of connected and automated vehicles. My contact information, these projects are funded by NSF, and then we are working closely with the Toyota Motor in North America. That's all I have. I hope I have a time to have some questions.
Okay, thank you very much, Dr. Brian Park. So this is a great presentation. And any questions from the audience here? So I do not see any from the chat box.
Be happy to follow up with the email if you are interested in. I have a couple of papers happy to share.
Okay, looks like no question. Okay, thank you very much again for your interest in the presentation on the topic of cooperative platooning in mixed traffic environment. Yeah, we appreciate your time, huh, Brian?
Thank you.
Okay, thanks. So now it's my great pleasure to introduce to you our next invited speaker, Dr. Xuesong Zhou. So Dr. Xuesong Zhou from Arizona State University is an expert in dynamic traffic simulation. You all know, probably used his software before, okay? And he maintains an open source mesoscopic traffic simulator called DTA Lite. Myself is a user as well. And traffic visualization tool, Nexta. As a leading open source developing team for USDOT, the Arizona State team has been developing a broader set of a seamlessly integrated open source computational engine. So DTA Lite has been applied in Maryland statewide model with 26 million agents, and open source tools have been downloaded by more than 20,000 times. So please join me in welcoming Dr. Xuesong Zhou.
Thank you. Dr. Fan, can I share my screen now?
Yeah, sure, please. Yeah, go ahead.
Okay, so I will stop the sharing. Change to the full presentation mode. Okay, great. So thank you for the invitation. I would like to report our current progress and the interest of the with the interest of the time here. I will go very quickly with about 40 slides. The title here is about automated vehicle modeling, and another what attractive terms is a digital twin. So how we can make this two working together, in particular, try to establish a good connection between the open data and our researchers and the city planners. So here is my report. Recently, We already know the terminology of the digital twin. Essentially, they are coming from 1960 computer-driven simulation. In 2000, they're simulation-based system design from NASA. And recently, thanks to the different companies, they try to promote the digital twin as a concept for the smart city. As I'm a transportation research team here, I would like to report the following 4 or 5 different small topics. Background on digital twin, how we can use the open specification of the GMS to build an open modeling community, and our effort of building virtual track-based micro simulation at the number 3, number 4. And my talk will be closed by a number of discussion on these critical research issues. So we know building simulation or building the digital twin are essential for the smart city planning. So how we can encourage the collaboration between OEMs, industry partners, researchers, and the planner. This is always challenge. How we can leverage the existing open source model, open data, for example, from OpenStreetMap to enable this quick decision intelligence. And more fundamentally, we are not just building a simulator. We need to look at how the gap exists between the multi-resolution modeling from aggregated macroscopic scale to carve-following model. So how to really bridge this gap is always a question for us to further pursue. We look at the open specification, open source data in the beginning, and I will try to just touch base on the high fidelity simulation framework we are building, and this will close out by the gap we try to illustrate. So when I try to build these different open source tools for the different agencies, they want the open source tools to be able to apply to different scale, and they want to use the open data in a standard to connect the different components, such as sensor data, transversion model, dynamic travel assignment, simulation, HCN, signal timing data. So how to maintain the consistency at the 2 levels. One is at the data standard level, the other is at the theoretical model level. This is always very challenging. So as I mentioned in the early introduction, we do apply the different tools in the statewide model of the merit, and has some different applications in the different cities. But the challenge is always case by case. It's difficult for us to apply that to a large scale or in a consistent way. Thank you for the recent effort in Rilett Foundation and the WOPI Center from USDOT, Federal Highway. They all come to the same agenda. Let's have a common modeling interface or specification for network. So I just encourage you to look at the Rilett Foundation GAMS data format, which cover macro, meso, micro specification of the network modeling, and it has excellent support for signal timing, and at least all the contributors and the committee members here. So with that kind of data format, we are able to transform this ad hoc connection in our open source tools to a more systematic system software coupling. Okay? I don't want to enumerate all the different components, but this gives us a good implementation foundation to move forward. So let me try to just have a list of the different tools in the last 2 years our team have been promoting. We use the OpenStreetMap data as a source. We have a tool, pattern tool as an OSN to GMS. This has been downloaded by more than 20 times now. The creator is our ASU PhD student, Jianming Lu. We are able to convert the whole United States OpenStreetMap network with 20 million nodes at the different intersections, and then later I can show you how we digitize that into the meso movement-based and the micro cell-based representation. We also use the land use data from OpenStreetMap to create the traffic zones and create a very quick way for you to establish the transportation demand between different zones. Milan, assistant professor from University of Jianming, we have been working very closely to create the Excel tool Sigma X to import the synchro data from the CSV format to the standard, and then we have a Python tool to create this compatible signal timing as a QEN for the quick simulation. We have our former PhD graduate, Dr. Peihen, to create this shortest path routing tool and the dynamic shuffle assignment tool and the Python package for using this standard to calculate different shortest path. We have our friend Dustin. He is a PC game creator for traffic simulator. His tool is much more popular in simulating all these two-dimensional, three-dimensional vehicle animation. And we are working together to promote this open standard together. So with all this pipeline, we have the category A as a network creation, B as a demand supply model calibration, C as a simulation, and these are all the available tools in the future so that you can see how the open data and open source tools can be worked very closely. D is something I want to highlight. It's easy to say different software modules, but it's difficult to look at the consistency between the demand and the supply and the further optimization. So my second topic I want to just report here is by using this OpenStreetMap as a data support, we are able to establish a multi-resolution network representation for CAV, simulation, and optimization. So we all know Sumo is one of the leading package now. They are using space continuous time discrete vehicle simulation. It has a very nice features. But the challenge for us is, as a researcher, we want to look at the opportunity for optimization, the opportunity for distributed traffic control. We want to have a more control on this network-based representation. I think as the excellent presentation by Professor Brian Park, we are also interested in incorporating this kind of tree or track-based modeling framework. For example, I list the statistic here. The train is a very safe vehicle transportation mode compared to highway driving. So what we do here is, thanks to the NSF support, we are able to map the physical road system into the different, we call the cyber track, and all the different cyber track will be represented in terms of lane changing, emergency response, car flowing, and this is the network foundation for us. So we are still in the progress of developing the consistent tool with the regional level representation, cell-based representation, 7 meters or 20 feet at our segment for the different small or medium scale networks. So if you're interested, you can look at our open source tool, Net2Cell. We are able to, for any city of the United States or any country, we are able to convert the macroscopic network from OpenStreetMap to the MISO dynamic traffic assignment simulation network with all the movement representing the traffic signal control, and to a cell-based network for you to model lane changing, and the car falling cases. So here is one simple example. You can see how the different resolution looks like, and a zoom-in view to show you how we can use the lane changing arc to control the potential conflict point and the potential point for us to optimize the model. If you look at this cell-based representation, you can model the lane changing as the route choice behavior to calibrate how the different routes being selected for a segment of the this freeway bottleneck. Okay. So I think many students will be interested to apply your knowledge of utility function to this case, how I select the different lane changing routes. So these routes are not link-based routes, they are the cell-based routes. And in the full consideration of waiting time, maneuver cost, and the estimated cost from a current point into the future. Okay. So with this third topic, I just talk about using the car following simulation platform. Actually, the most interesting research question we have is how we ensure consistency. I have different network representation. Different network have very different characteristics in terms of flow, density, in terms of the trajectory. So we always want to go back to the root of our development for the physics or for the larger scale system. We need to have simple car following model, simple traffic flow model, simple volume delay function to explain the reality. I think the excellent example we all know is the derivation between consistent Greenberg, flow density relationship with the car following, the third GM model. I don't want to enumerate all these derivation for you. Just try to make sure we know there's a consistency from the very early on, the consistency between the fundamental diagram of VK relationship and the car following model. So in this research direction, my team has been working on the different traffic flow fundamental diagram calibration. Recently, we promote one of the 3 parameters, which is called F3, to calibrate this traffic flow model with free flow speed, congestion speed, and one of the parameters to adjust the capacity. So this paper has been published in Transportation Research Part B recently. Using only 3 parameters with a very parsimonious model, we are able to adjust the degree of flow reaching the optimal capacity. We can use an example of the different city with a mixed traffic condition, how the capacity can be reached with a different mix of the vehicles. That model has a very consistent car following form, and with a different n as a coefficient of the capacity maximizing, we are able to show that if we have 2 things in mind, car following model and the speed density relationship, we are able to design the one coefficient to control the output of the capacity or the flow discharge rate and the detailed car following model in our traffic simulator. So we are able to calibrate this model for a long corridor along US 101. And at the current stage, I'm happy to report that our proposed revised model is able to produce almost one of the best results across the different regimes. So another topic I always want to discuss as a closing here is volume delay function. Volume delay function has been there for almost 60 years, and we need to understand the volume delay function typically has a difficulty to deal with V/C ratio greater than 1. So by using this fundamentally important concept of the capacity, we try to measure the congested demand in this V/C function. So to illustrate that, I try to show using this example. We use the speed and capacity from our fundamental diagram as a cutoff value, and then we can define the congestion period precisely because the T0 and the T1, and then we use the corresponding volume to calculate the congested demand. So by doing so, we are able to overcome the previous issue of V/C greater than 1. I also want to just raise the awareness of excellent research by Dr. Moore in 1982. He was able to use a polynomial arrival curve as a foundation to derive what is related traffic delay function. So due to the interest of the time, I'm not going to go through all the details, but essentially is once you have a quadratic inflow rate, a constant discharge rate, you will be able to define the congestion duration very precisely and to determine the key parameters of first order, second order approximation, and then derive a form very similar to BTR function. Here, alpha equals to a certain functional parameters, the beta equals to 3. So the reason the beta equals to 3 is the polynomial arrival curve is quadratically distributed. So it's a second order arrival curve. So as we know that the beta typical equals to 4. So recently we are using this approach, and with the extension, we are able to promote a new type of cubic polynomial arrival curve, and we can use that to approximate very nicely the time-dependent travel time, time-dependent queue length, and here I try to show some early preliminary results along Interstate 395 in Washington, D.C. area. So the key message is we need to apply calculus into our simulation. Agent simulation is not sufficient. We need to try to use these high fidelity analytical forms to establish a consistent representation. So here is one more slide to show you, our current progress of applying the dynamic travel assignment model for the Washington, D.C. area. So with that, I think now my message is clear. Let's try to work together to use the open data standard, open source tools to build the data foundation, consistent data foundation. And then we can look at the system multi-resolution modeling tools to build the essential consistent representation across different resolutions. And the last step is to build a digital twin for decision support. We can use that for many important applications of programming of the projects, planning of the long-term initiative. So with that, I would like to just close my presentation. Thank you for this great opportunity. And our SU open source teams are always interested in collaborating with the different researchers, planners. I think with the good theoretical foundation and the open specification, we can do something much more exciting and something great into our future. Thank you.
Okay, thank you very much, Dr. Zhou, for your wonderful presentation. Very helpful introduction of the open smart city digital twin tools and applications. We appreciate your time and support. So any question from the audience for Dr. Zhou?
If not, I always encourage you to search GMS data specification. Our goal is to outreach different professors at the different universities. We want to deal with all these larger scale modeling, but we can help you to build your mini digital twin of your campus. This will be a great asset for all the students to learn the insights and to leverage all the research results we are talking about. Thank you so much.
Okay, thank you again, Dr. Zhou, for your great presentation. Okay, now it's my great pleasure to introduce you our third invited speaker, Dr. Lily Du. So Dr. Du is an associate professor in the Department of Civil and Coastal Engineering at the University of Florida. Dr. Du received her PhD degree in decision science and engineering system with a minor in operation research and statistics from RPI back in 2008. She is a recipient of the NSF Career Award in 2016. She currently chairs TRB subcommittee on emerging technologies in network modeling and ASCE artificial intelligence in transportation committee. So please join me in welcoming Dr. Lily Du.
Thank you for Way's introduction. So let me start my presentation. Could I share my screen?
Yes, please. Yeah.
Okay, can you see my slides correctly?
Yes, we can.
Okay. So yeah, thanks again for with introduction, and good afternoon, everyone, or good morning, good evening, depends on where you are. So it's my great pleasure to share our recent study titled as a System Optimal CAV Platooning Control for e-driving at signalized intersections built upon hybrid MTC system, online learning, and distributed optimization. Again, this is Lily Du, and I'm a social professor at University of Florida. This research is supported by NSF and also Toyota Infotech. At the beginning, I want to use this camera to build up some concept regarding to platooning centered control. So most likely in the future, vehicle will become very fancy and it's connected and autonomous vehicle, and the vehicle driving on the road. And we think that they will have some intent to form a platoon. So, and take advantage of this platoon, people can relax and move more efficiently and smoothly. However, we can see that, we need to deal with different scenarios, such as we need to have to enable one vehicle join to the platoon smoothly. And also at some point, we will say, some vehicle may have different journey and they need to leave the platoon. We have to have the platoon have the capability to enable this kind of request. So this is the, I will stop the video here and move to the presentation. So with this concept, that the main things I want to mention, I want to raise is we want to do platoon-based traffic control or platoon-based driving control. So with this idea, what we think is each individual platoon actually would be considered as a unit or system. And then we develop platoon-centered driving control to instruct the movements of the platoon and the different scenarios. This will include car following behavior, and also maybe two different platoon want to cooperate their movements, and also lane changing requests, as well as platoon merging and splitting. And we also want to consider how this type of when platoon and this kind of platoon-centered driving approach to intersection, then how this platoon can go through the intersection smoothly. So of course, for the presentation today, I'm not going to cover all the scenarios we started, and I will mainly focus on some of them. At the beginning, we start with a very simple scenario that is a pure CAV platoon, and we want to control its car following behavior so that this platoon can move smoothly, efficiently, and safely. And to do that, we developed a centralized MPC. I will introduce MPC control later. Basically, the centralized MPC controller will develop the movement instruction for all the vehicles in one platoon systematically and optimally. And we also noticed that, for vehicle platoons driving on the road, it is a self-organized system. There isn't a centralized unit can help to do this kind of movement control. So we further develop this approach as a distributed optimization and algorithm. Basically, we will split the computation load to individual vehicle, and they will work together to generate the system optimal movement control and make the platoon move with the objective we desired for the centralized MPC control. And this work has been published in Transportation Research Part B, and the reference is given at the bottom of this slide. And after that, we move to a little bit more complicated scenario as we consider a mixed flow. And in this mixed flow, there are two platoons, basically a leading platoon A1 and then the following platoon A2. These two platoons are distinguished by a human drive vehicle platoon. So we would like to cooperate the movement of these two platoons so that we can make the traffic smooth and efficient. To do that, and build upon the PCC we developed for individual platoon, we noticed that the very important issue is how the following platoon can predict the movement of the first leading platoon by considering the delay generated by the human drive vehicle. So to address this problem, and our study will develop some online learning algorithm so that we can learn this kind of delay generated by human drive vehicle on one adaptively and transfer this kind of delay to the following platoon A2 so that they can respond to the movement of leading platoon A1 efficiently with the consideration of this delay. And this work and actually is also published in the Transportation Research Part B and showing on this the bottom of this slide. And we also, I just briefly show the experiment result by which we compare this kind of cooperative PCC with non-cooperative PCC. This is non-cooperative PCC. That means we implement our PCC for this individual platooning control without build up any collaboration. And then we also compare our PCC control with the CACC control and also the field data. From the result, you can see that the cooperative PCC work actually provides the best performance for smooth traffic speed and also dampen the traffic fluctuation. And further, we want to move another more complicated scenario that is if a platoon and our PCC control moving approach to an intersection, then how we can manage the trajectory controller for those platoons so that they can go through intersection smoothly and efficiently. And to do that, we will develop a hybrid MPC system to do that. At the beginning, once the platoon, the mixed flow platoon is approaching to intersection with certain range, they can communicate with traffic signal. And we need to decide if this, if with a given left green time, we will decide if this platoon entirely can pass the intersection or not. If not, and we will develop an optimization model to find the best splitting point so that along that splitting point, we can separate this platoon to a platoon A1 and another platoon A2. And then we will develop different PCC controllers, basically MPC Q1 and Q2, and get these two platoons go through the intersection in a sequential green interval. So, so far, all I talk about is just mainly about our conceptual idea. And the next, I'm going to move to the math part and to show you how we implement those ideas mathematically and rigorously. At the beginning, I want to give a little discussion about MPC control. And this is a closed loop discrete control, and it's going to implement it every second. And the main idea is, at the beginning, we given system state, basically it's a platoon moment state, and also the current control input, and we are going to predict the moment of the system in the future. with the predicted output, basically the Platon moved in the future, we can mirror the control and the system performance and errors. And those kind of feedback will put into an optimizer with the, this is a constant optimizer, basically consider system performance and safety, acceleration, speed limit, all those kind of constraints. This optimizer will generate the controller input for the next step with the prediction of the system in next P step. So basically, once we, the optimizer generates the P step control, but only implement the first step for the next time interval. So this process will repeat at every second, and to ensure the system can resist the disturbance of the environment. And all our PCC control will build upon this kind of MPC approach. So with understanding of the MPC approach, and we first want to introduce a prediction model. Basically, it is the vehicle dynamics. And for the class I mentioned, that we worked on the mixed flow Platon. So, and for CAV longitudinal dynamics, we use double integrator model to describe their moment. And this is standard, but a new point I want to mention is in our vehicle CAV dynamics model, we involve a random variables. This is delta U here to capture the uncertainty resulting from vehicle powertrain delay or aerodynamic drag. And this will definitely cause some difficulty for us to, in the future, to ensure the control stability and feasibility. And we developed some mathematical proof to ensure it. And next is for the HDV, I think, we use the no-well car following model to estimate the moment of human drive vehicle. Of course, we all know that. And the two critical parameters that is represent the reaction delay and the distance delay actually is going to vary according to different human drive vehicles and the different type of driving scenarios. And they are not constant value, actually represent another level of uncertainty for this kind of Platooning control. And for our study, we are going to learn and update the value of these two delay, basically displacement for our MPC model at each control step using an online learning approach. I will introduce this online approach later. Next came to our MPC control. The first one is our MPC control Q0. Actually, it is the we will mainly talk about the optimizer involved in this MPC Q0. And this MPC Q0 will help get the Platon moving close to the intersection. So the main idea is the objective function will consider the speed, the spacing error, the speed fluctuation, and acceleration input. They will respectively help traffic smoothness, riding comfort, energy saving, and emission reduction. And regarding for the constraint, the first one is standard. It means the speed and acceleration will be limited in certain kind of bound or limits range. And for the safety spacing, and here I want to particularly mention that we will use the adaptive safety spacing constraint by factoring the leading vehicle speed and the relative speed between adjacent vehicles. And this adaptive safety spacing will help us efficiently use road capacity in the urban traffic condition. And accordingly, the same idea we will apply to the objective function, develop the adaptive desired space in the objective function to mirror the spacing errors. And I want to particularly mention that in the safety spacing and adaptive desired spacing formulation, we will involve some parameters such as delta 1, delta 2, and delta, and to ensure the control stability, feasibility, and also control and the Platon smoothness. And with that, once we build up MPC Q0, build upon MPC Q0, we are going to develop our MPC Q1 and Q2 if you remember that MPC Q1 and Q2 will be used to get the Platon, the splitted Platon A1 and A2 to go through the intersection sequentially. And so the first one is MPC Q1 will get the first subplaton to go through the intersection. To do that, build upon the MPC Q0, we will add one more constraint as I marked by the blue box, and it will ensure the subplaton A1 to pass intersection at the end of the current green interval. Yeah, please note, and once the subplaton A1 pass intersection, this constraint will become inactive forever. Then it can be, then the MPC Q1 will directly go back to the MPC Q0. And with this way, we can smoothly connect the MPC Q0 and MPC Q1. And the next is we develop another MPC, is MPC Q2, which will help us to ensure that the second Platon A2 not going to pass intersection with current green interval, but next green interval. To do that, we add one more constraint here. And again, once the current write lines running out of time, and our control for the Platon A2 will take off this constraint. Basically, we relax this MPC, the optimizer of this MPC. Then this MPC Q0 will directly go back to MPC Q0. This MPC Q2 will go back to MPC Q0 again. And if the second Platon A2 can go through the intersection with current green interval, then they will go through the intersection under the control of MPC Q0. If not, this A2 will go through the splitting and the parsing process as we just did in last interval, the next green interval. So next is I want to introduce optimizer that actually is the MNLP for us to find the optimal splitting point for that long plateau. And again, this MNLP is built upon the MPCQ0 optimizer again, but include as objective function, we include one more factor to maximize the traffic throughput. Basically, we want to minimize the length of the second plateau. That means that plateau has to wait for the next green interval. In other words, we want to fully use the current green interval. And then, besides the constraints regarding safety, speed, and acceleration, and we introduce binary variable y to represent the splitting point and also the corresponding constraint, so that we can make sure that the plateau is only split before a CEVI, because we cannot control human drive vehicle, so we are not supposed to split the plateau before a human drive vehicle. And also, we want to make sure that the splitting point we choose can make the leading subplateau A1 go through the intersection with the current green interval, while the following subplateau A2 cannot pass the intersection until the next green interval. And I want to mention that this optimizer for finding the optimal splitting point has to be solved in 1 second, so that we can smoothly switch our MPC controller Q0 to MPC controller Q1 or Q2 with the by ensure the controller continuity. So this creates a huge computation challenge, and our previous study has developed a distributed algorithm we label it as MDDB. And with this distributed algorithm, we are able to undertake this task very well. And now I want to talk about the algorithm we are going to use to solve those MPC Q0, Q1, and Q2. So our approach is titled as active set-based optimal condition decomposition. Okay, from the title, we can see that this algorithm actually includes 2 parts. One part is we identify active sets. The other part is we use optimal condition decomposition approach to find the solution for the constraint with active set. The idea underlying this algorithm is that we notice that, in most of the time, not many vehicles will drive with the maximum speed or maximum acceleration deceleration, or most of the time vehicle won't drive at the boundary of the safety constraints to risk their safety. So with this kind of observation, it actually means a lot of constraint in our optimizer is inactive, okay? And for the optimization problem, if we take off those inactive constraints, it's going to make the optimization problem much easier to be solved. Mainly, they actually can be solved by Newton approach, because once we take off this inactive constraints, the optimization with only equality constraints will, have the condition. They are a set of equations, or basically a system of equations. The system equations can be efficiently solved by Newton method. So this is the approach we think about active set. And however, as I said, the Platoon is a self-organized system. We don't have a centralized approach to implement this Newton algorithm to solve this problem. And we want to distribute this Newton method. With that, we developed our optimal condition decomposition approach. Basically, by taking advantage of the structure of the mathematical model of this problem, we decompose the computation into individual vehicles so that we can use distributed computation to calculate the to find the optimal solution of each optimization problem with only active set. And this is the main idea. So the step and the flow chart was shown in these slides, and I probably want to quickly go through them. So at the beginning, we have the empty active site, and then we use OCD approach to solve the optimizer of this MPC with only active constraint site. This step actually just repeat the step shown on the slide. Step one, we find the direction. This actually solve a set of equations, basically linear equations. And then we update the primal variable and the dual variable. Based on the sign of the dual variables, we are able to find that which constraint side should remove from the active side, because if we make it inactive, it actually help us improve the value of objective function. And at the same time, we will identify some other constraints that should be involved in the active side. This process repeat until we find the solution satisfy our convergence condition. Oh, sorry, and yeah, and now we are done about introduce all the MPC model. The next step, I want to introduce our online learning approach. Basically, recall that to develop the collaboration between two PCC-based Platooning control. And we want to have CEV in the picture, as the example shown in the slides, we want to have the CEV n+1 predict the response delay of the human drive vehicle M hat to the moment of CEV n. And using the historical trajectory data, this CEV n and the CEV n+1 can collect it. And of course, we don't know the delay, and their aggregated value involve unknown number of human drive vehicles. And traditionally, we can use curve matching algorithm to solve this problem. However, when we implement this approach to the urban street, and this approach won't work very well because it needs a long warm-up time. And for the relatively short street, and we are not able to do that. And so we think about to develop a new adaptive online learning algorithm. To do that, we have the observation that if the vehicle does not vary in their speed very much, then the parameter we use to match, the two displacement we use to match these two curves, basically CEV and HDV hat, we will have multiple choice. As the picture shows, you can either use the blue box or use the orange box or yellow box. However, if the Platoon or the vehicle has speed variation, then at the turning point, you only have one choice. to determine these two parameters so that these two curves can match very well. With this observation, our algorithm, actually involve two new factors. One is we weight the speed variation, and the other is we weight the current or recent trajectory data more. And I want to use this slide to show the main idea for us to develop this adaptive learning algorithm. At the beginning, we have the initial value for the weight and also the two parameters. This basically this time and the spatial displacement. And then we want to learn the best parameter, basically the two displacement according to recent trajectory we collect for CEVN and HCV hat. After we have this kind of, by the way, because we only use the recent trajectory, so this actually can be done very efficiently. And then, once we have the two parameter estimated with the recent trajectory, we are going to combine the current estimation with historical estimation together using the formulation we gave on the slides. You can see that we give latest trajectory and estimation higher weight. And we also involve some feedback error involved in the equation to further improve the estimation accuracy. And we repeat this step 2 and step 3 over the entire period of the MPC control. By the way, this adaptive learning process will integrate with MPC control at each time step. And then use the slides, I want to show the numerical experiments to say how efficiently this algorithm we developed to implement our MPC control. Then we can see with a long prediction horizon P equal to 60 seconds, and our ASOCD algorithm can efficiently solve the problem within 1 second. And at the same time that the MDBB algorithm can help us to find the optimal splitting points also within 1 second. And the next is, I want to use these numerical experiments to show the merit of our PCC-based e-driving. And you can see that we compare our approach to the CAC's approach in the literature, covering the scenario that the Platon will meet green interval or meet red interval. And the results show that our PCC-based e-driving can smooth the traffic much better than the CACC, and they significantly save the emission and energy consumption. On average, it's about 60% above or low, depends on it is on green interval or red interval. And we also compare our approach with some other e-driving algorithm developed in the literature, such as the POPs SOS. And their approach manage vehicles reach to the desired space before the intersection, then pass the intersection with those desired space. And you can again see that our PCC-based e-driving can give much more smooth traffic trajectory control, and they save the emission, energy consumption, and the travel time, and both green interval scenario and the red interval scenario. And with this, I'm done about the presentation for our scenario that Platon goes through the intersection. Next, I will present one more scenario that is AI-aided the cooperative lane change for Platon and the TCC. So once a Platon driving on the road, it's very possible there are some other vehicle want to cut in and or merge into this Platon. Or our study is we want to give the Platon-based control so that the Platon can smoothly split at some point, and that those two vehicles move in. And to do that, our first consideration is that the lane change request should be sent by this subject vehicle, and then the Platon need to decide, what's the best spacing and timing to accommodate this request. To find this optimal spacing and timing, we consider that the Platon is under certain kind of features such as speed, spacing, number of Platon, and this kind of thing. And with this as the input into some machine learning model, and we can roughly estimate the potential candidate spacing and the timing for these two vehicles to cut in. Then combined with optimization model, we can find the optimal spacing and timing to accommodate these two subject vehicles. After that, we will, sorry. Oh yeah, after that, we will implement our PCC control to enlarge the position of the best spacing so that the other two vehicles can smoothly cut in. So we compare our approach with the field data. Actually, we also compare with some other lane change control algorithm. Here, I only show the result compared with field data. Then we can see that this PCC-based collaborative lane change control can smoothen the lane change accommodation and also reduce traffic fluctuation as you compare with the field data. And also you can see that the Platoon actually can very efficiently to find the best point and then light the vehicle cut in. You know, you can see in the second picture in the first column, you can see the Platoon, the lane change request actually is accommodated in the first second after the request is sent. However, in the field, it takes a longer time. It's accommodated at the fifth or sixth second. So with this, it came to the end of my presentation. Thank you very much for your attention. I'll be very happy to answer all your questions. And I also want to acknowledge the contribution of my co-author, my student Hanyu Zhang, and also my previous students, Siyuan, and my collaborator, Jianming. And this research is supported by NSF and to tie Insight. Thank you.
Okay, thank you very much, Dr. Du, for your great presentation on the operation research application in the CFE research field. So in the interest of time, if any of you have any questions for Dr. Du, you're welcome to contact her offline. So we're going to move on to the last but not least presentation. So it's my great pleasure to introduce to you the last speaker, Dr. Jianming Ma. So Dr. Ma holds a Ph.D. degree in civil engineering from the University of Texas at Austin. So hook'em horns, huh? So he coordinates connected and automated vehicle activities at the Texas Department of Transportation, whether demonstration, pilot projects, national study, and university research. He served on multiple national committees as either chairs or research coordinators for SC, TRB, and AASHTO, etc., and won many exceptional leadership awards. So the title of his presentation today is Texas Connected Freight Corridors. Now, please join me in welcoming Dr. Jianming Ma.
Oh, good afternoon, everyone. Can you hear me, Dr. Wei?
Yeah, we can. Yeah.
Okay, good. First of all, I apologize for the last minute change, and I want to thank Dr. Brian Park, for being flexible and switching with me. Really appreciate that, and also would like to take this opportunity to thank Dr. Wei and his group and for the invitation and for the opportunity to share what Texas has been doing in the deployment of connected vehicle technologies. I know the previous speakers, you guys talked about a lot of like CAVs, in theory and do the simulations, trying to quantify the benefits, like increase the throughput or improve the safety. So this project basically we're trying to take whatever you guys have done, found and from the theory and trying to deploy it in the field and mirror the benefits, see if how it's going to work, trying to get ready for large scale deployment. So today, I'm going to talk about a Texas Connected Freight Corridor project. So this is one of the largest connected vehicle deployment project in Texas. So the idea is to implement, the connected vehicle technologies in the Texas Triangle. I know the Texas Triangle is one of the 11 mega regions in the States. So the population is gonna grow. Right now is we're in Texas. We got like in the Triangle area. We probably got like about 27 million people, and in the next 20, 30 years, it's gonna close to be doubled. So we're gonna have a lot of people, and associated with that growth, we're gonna have important freight and other economic opportunities. How we're gonna address that? So basically, we're trying to leverage the connected vehicle technology to help us to address some of the safety and mobility challenges. So the triangle is, and I know you can see it from the map here on screen. It's basically that's the interstate I-35 from Dallas-Fort Worth area all the way to the Laredo. That's the Coahuila. That's the Mexico. Basically, that's the Laredo is a border city. And then the I-10 from San Antonio to Houston, then I-45 from Houston to Dallas. And there is a little bit stretch. It's called an Interstate 30. So that's between Dallas and Fort Worth. So these are the highways that we're working on. And the goals basically, our hope. We through this project, we're trying to improve the safety. I know you probably heard the latest press release from USDOT. Due to the pandemic, a lot of people and we're seeing like a traffic travel is kind of decreasing, but and the people driving tend to speed a lot. So the speeding and people not wearing seatbelt are the two major reasons for the increased the fatalities in the US. Right now, we're kind of in a 20-year high. So our goal here is trying to leverage the connected vehicle technology to improve safety. And similarly, connected vehicle, with that connected vehicle, we can exchange information freely between the vehicles and basically our truck drivers and TMCs and other sources. So it will help them better improve their decisions regarding when they travel and how they travel, where they're gonna travel. So that will enhance their mobility. And there are some other benefits, like I'm not going to go through the environmental benefits. We can implement it like CACC, just Dr. Du just mentioned. And we're deploy some of that advanced technologies like cellular V2X, 5G. Trying to leverage this new communications technology to improve the connectivity. And last but not least, through this deployment, hopefully we can create an ecosystem that would facilitate the further economic opportunities, regardless it's a new in a business or our continuation of our workforce development. That's kind of the 5 goals that we're keeping in mind while deploying these projects. And there are some immediate benefits for doing that. Like, for example, with the deployment of connected vehicle technology on the triangle, so our free partners will be able to get access to the real-time information on work zone situations, traffic queues, and other safety critical warnings, alerts, and also this kind of a pilot. It would allow us to explore the different deployment models and trying to see, hey, if this is gonna work and what kind of situations we're gonna we need to address, those type of things. And last but not least, through this process we can develop associated standards and specifications, set example for future large-scale deployment, and hopefully to contribute that to the national policies and rules, those type of things. This project is funded through minimize this one, through USDOT's ATCMTD grant. It's Advanced Transportation Congestion Management Technology Deployment project. It's multiple words. But that's kind of a program that USDOT really initiated to fund projects, especially emerging technology project. We're Texas Department of Transportation, we're a recipient of that project. And we are working with our 3 partners, Texas A&M Transportation Institute, Southwest Research Institute, as well as UT CTR, Center for Transportation Research. And this project includes like 3 phases. The first phase started in like 2 years ago, 2019. Basically, we're doing some high-level design, planning, CONOPS, and those type of things. And we're currently in the second phase of the project. We're doing the detailed design, like app development, procure security credential management systems, and we also develop like a connected vehicle data framework, and we keep engage our stakeholders. And then the third phase will be like once we get these applications loaded onto our OBUs, which will be installed in trucks on the trucks, and RSUs. We're gonna install along our triangle we just mentioned, and we're gonna do some like operations, data collection, and do the evaluation to see how well these applications perform, and how truck drivers or end users perceive these. So this is basically a high overall overview of our project timeline. And so this is a little bit summary about phase 1. So the phase 1, we basically which is engage our stakeholders. Our stakeholders include like the public sector stakeholders, private sector stakeholders, as well as the associations. Basically, for the public sector, because this triangle covers 9 textile districts, so we have like 25 districts in Texas. So 9 of the 25 districts would be covered by this triangle. And also we have very good relationship with our regional partners like NCT COG, basically it's a metropolitan planning organization in the Dallas-Fort Worth area. We also work with our local cities and counties and other state agencies like public safety, Department of Public Safety. So we work with them and trying to get their input, what their pain points are. And so, and then the private sector, the next one is a private sector partners. So we got our HEB. For those of you who lived in Texas or know, I've been to Texas, HEB is the largest grocery chain in Texas. So they have their own fleet. So we work with them in their fleet, basically, going everywhere in the Texas. So we work with them and trying to instrument their vehicles, and create carrier as a national carrier. And Too Simple is basically an automated truck developer, and Kodiak Robotics is also automated truck. They are running their trucks here in Texas. And we also have some industry affiliates like Ford, and there's some telematics, because these trucks, they have like electronic login devices installed under cabinet. So they use different manufacturers, the device like a Geotab, Omnitrax, and others, and an application developer like Drivewise. And some of you probably be familiar with the Drivewise. Drivewise basically is an app, like a travel information app that provided specifically for the truck drivers. And we have also engaged in other sectors, like for example, Texas Trucking Association. They have a large pool of membership, and so through them we can reach out to a broad community of the trucks. And so with these input from the public sector as well as the private sector, so we identified some applications. So we are developing to implement. So for example, originally when we put proposal together, so we proposed like 12 applications, but through the development process, we feel that, hey, these are these applications that are in the red boxes. So they're the ones that our partners are most interested in. So we decided to focus on these 5 applications, and they're like again, it's not just that we do it. This is a kind of like a basic consensus that we reached through the both private sector as well as the public sector. And so like we also recruiting this, these are the stakeholders here. I think I mentioned a little bit. So we got, for example, the partner trucks, they contributed like 430 to about 400 over 400 trucks they're contributing to for this project. And we're also gonna equip, because not every we have a limited budget. We can't just put OBUs on 400 trucks. So we're gonna deploy between 50 to 100 OBUs on the trucks, and for the rest of the trucks, we're gonna utilize. We're gonna basically load our applications. Remember the 5 applications that I just mentioned, load to the Drivewise platform. So we're working with Drivewise. And the Drivewise is kind of an application on the ELD. ELD basically is just like a smart device on the on the trucks. So they gave the truck drivers a lot of other capabilities. So that's kind of a thing. And we also work with our local partners as well as Tactile District, identify the exact locations where we're going to deploy RSUs. These are the sample site that we're about to we identified to deploy this. And then the phase 2 activities were here. So basically, as you can see, we're procuring like OBUs, RSUs, OBU like an onboard unit, RSU roadside unit, and we're also developing these 5 applications, and we're procuring security credential management system, as well as we're developing. Initially, we're going to procure the connected vehicle data framework, but after researching the market, we feel that it might be better to develop our own instead of procuring some, the market solutions that's still to be matured. Then we are working with our partners and trying to prepare how we deploy them and do some like a training. Like next week we're gonna have 2 training sessions, one for public sector stakeholders, and another training for the private sector stakeholders. Basically, for the public sector stakeholders, we develop training specifically for our operators, like especially from CAMMSE traffic management centers, how they manage the RSUs, how they gather data from RSUs, how they perform like a monitoring of the devices and those type of things. And the private sector training, basically we're gonna train them how to, once we installed our OBUs on their trucks, how to use it and how to maintain it, and we're gonna and how we get a data out of it, because for evaluation purpose. And that's basically the main tasks, but we also have other stuff that's going on. And these are how we identify these locations and what kind of applications we're gonna deploy at these locations. For example, this is a kind of a HEB warehouse center, and this is a kind of a local street. This is I-35. They're like, this is like, their center, basically the warehouse over there. And we feel, hey, this, a lot of trucks, they're traveling along here and trying to get on the I-35. So we feel that, hey, for these signals, so, if we could implement a free signal priority, give like priorities to the free trucks, it would help us to address, some of the mobility issue, as well as we get some benefits, because if trucks they have a few stops, they're gonna have less emission, those type of things, and also queue warning is one of the applications that we plan to deploy along this this stretch. And these are the devices, for example, right now we're using a CV2 cellular V2X vehicle to everything. Many of you are probably aware that CV2X is kind of a technology that we're moving towards to, because before we have been using the DSRC, dedicated short range communications. That's been being researched and piloted, and some of the states, they have deployed DSRC units and to implement, like, for example, transit signal priority in the Utah and in Salt Lake City. So in this project, so we're gonna mainly focus on the CV2X, but some of the RSU units we are getting will have a dual mode. Like dual mode means they can broadcast both CV2X and as well as the DSRC. And these are the in-cab telematics providers that we mentioned. We're working with. We're not directly working with these guys, but we're working with Drivewise. And Drivewise, basically, they have the contract relationship with Omnitrax, and Drivewise, basically, we incorporate our applications into Drivewise, the bigger app system. Then they install the Drivewise on these Omnitrax, so we can disseminate alerts, warnings that we wanted to, and to the truck drivers, like, for example, the work zone warning and queue warning, those type of things. And this is kind of a data framework, because this is our TMC software or system, advanced traffic management system. We call it Lone Star in Texas. I know Florida, they call it Sun Guide. It's basically the same thing. And so there are like these are the three different scenarios. Like one, we're gonna talk to our RSUs in the field, and then RSU talks to OBU on the trucks. And so basically that's a kind of a direct communication. And the second one, given we're still very low in equipped vehicles, like connected vehicle market penetration, especially for the CV2X enabled connected vehicle, they're still low. So, but we wanted to make sure the benefits that we are going to get from this connected vehicle technology can be enjoyed by a bigger, in a fleet. So we decided to, hey, how about we disseminate through this connected vehicle data framework. And under this approach, we have two different paths. First path, we can, the connected vehicle data framework directly talk to the ELD, electronic locking device, that's on the trucks, and another path is through the third-party app. In this case, we're working with Drivewise, so we're gonna basically, the Drivewise, it will get data feed through API. From us, and then they process and then they disseminate that information through the ELD, and also a security credential management system, because that's the kind of important piece we wanted to incorporate into this deployment, because this in a real world, so you have to ensure that everything you disseminate, how do you know, the messages or the information I received from RSUs, they are from a trusted source, because nowadays, this kind of a network, information security, cyber attacks, cyber security, those type of things, they're not unusual, they're here every day, It's just like any computer system, if for example, the connected automated vehicles, they're leverage this kind of information or alerts, warnings to negotiate these automated vehicles. So if something like, for example, if a hacker get into the system, send like fake messages or just block the true messages from being sent, that would create a life-death situation. So that's why we wanted to, in the first place, we wanted to implement this security credential management system to ensure that all our information or alerts, our messages sent through the RSUs and OBUs, they can be trusted, in that system. So. And this is just an example of the work zone warning and what's look like in a cab, what it look like in a TMC, and so and that's kind of the second phase. And the third phase, next step, I would say, next step is we're gonna wrap up with the application development, and we're also gonna finish up the connected vehicle data framework, and we'll also work with our not free partners, our textile districts, trying to do site visits, because we identified the locations. We had to do the site visits due to COVID. We didn't do. We were not able to do much travel, but we're gonna do like a virtual site visit, use because Google Street View, and then we can go down to the the site to see if this site is really the ideal site, and also we're gonna work on, hey, how many of these RSUs, OBUs will be assigned to each of the districts, each of the location, as well as we have a bunch of free partners. So how many OBUs each of the free partners will be getting, and we also do that training, so trying to get them ready for the deployment, and that's last but not least, we're gonna do after we installed all the systems, so we're gonna operate the system, gather data, and evaluate it, because in the first phase, so we develop an evaluation framework, and so we're gonna gather data and evaluate how well these systems will perform. And basically, that's kind of a quick overview of our connected vehicle deployment projects in Texas. These are the major main contacts. I'm the project manager on that. We got Seymour from TTI, who's the lead for the TTI team, and Eric Thorne from Southwest Research Institute. They're mainly develop the applications, and Chris Chen from the UT-CTR. She and her team are working on the stakeholder engagement and performance evaluation. With that, thank you very much. I'm not sure I may exceed the time limit. I really apologize for the delay. I'll just turn it over to Dr. Fan to see if there are any questions.
Okay, thank you very much, Dr. Ma, for your very informative presentation on TxDOT connected freight corridor. So we're going to see whether we have any question from the audience at this time.
There's some chance here.
Okay. No question? Okay. So once again, I would like to thank all of our invited speakers for their insightful presentation. We really appreciate your support and your time as well. So thanks again. So now at this point, I see Dr. Mockmel is here, who will be moderating the next session, technique session on connected automated vehicle and machine learning application. So
yes, sir,
Dr. Mockmel, how would
yes,
you
sir.
like to go about next session? You want to take a break or just directly?
Yeah, I think we'd probably be good to take a 5-minute break.
Okay. Okay, sounds good. Yeah. So we will see everyone again at 3:35, right?
Sure.
Okay. Thank you all. Yeah.